Hello, everyone. Some of you have been asking me during the break about solutions to the last set of homework exercises that we had, set 50 and 51 on page 330 of our text. And since we really didn't get a chance as a class to go over a lot of exercises like that, I'm going to do solutions to some of the exercises that you've asked me about in the text. The first exercise is exercise 21 on page 30. And here's an observation I want to make about the integrand. It's the quotient of polynomials, and the degree of the numerator is greater than the degree of the denominator. Any time that we have an integral where the integrand is the quotient of polynomials and the degree of the numerator is greater than or equal to the degree of the denominator, the thing to do is long division of polynomials, to write this as a polynomial plus a quotient of polynomials where the degree of the numerator is less than the degree of the denominator. So that's our first order of business. And we can either do long division of polynomials or synthetic division if you know how to do that. So let me write this down. X to the fourth plus x minus 4 over x squared plus 2. And I'll write my divisor, x squared plus 2. And I'll write my dividend, x to the fourth. And when I write my dividend down, I'll make sure that every power of x has its own space here. So I'll have x to the fourth plus 0x cubed plus 0x squared plus x minus 4. And to perform the division, I'll compare the terms of highest degree of the divisor and the dividend. X squared goes into x to the fourth, x squared times. X squared times x squared is x to the fourth. X squared times 2 is 2x squared. And then we'll subtract, just like in regular division. And we have negative 2x squared plus x minus 4. And we repeat the process. X squared goes into negative 2x squared, negative 2 times. Multiply negative 2 times the divisor, we get negative 2x squared minus 4, I hope. Let's see, negative 2x squared minus 4, yep, looks right. And we subtract and we get x. X divided by x squared plus 2 is x divided by x squared plus 2. Multiply this by our divisor and we get x. And we're done. So x to the fourth plus x minus 4 over x squared plus 2 is exactly the same as x squared minus 2 plus x over x squared plus 2. This is the expression that we want to end up computing the antiderivative of. We have a quotient of polynomials here, but the degree of the numerator is less than the degree of the denominator, so we can handle that. Give me a second to erase and create more board space. Okay, I'm back with a little bit more board space, and I have my integrand rewritten, and I can compute the antiderivative of this thing. And it's the sum of three terms, or sum or difference of three terms. So I compute my antiderivative term by term, one term at a time. Antiderivative of x squared is x cubed over 3. Antiderivative of negative 2 is negative 2x. And antiderivative of x over x squared plus 2, holy moly, I'm going to have to give that special consideration. So I'll just write the antiderivative of x squared plus 2 dx. And when I finally do figure out what this thing is, then I'll add my plus c to the very end. I didn't add the plus c yet. I only need to add 1. So I'll wait until I compute the antiderivatives of each term, and then I'll add my plus c at the very end. Now this thing here, I'll tell you what jumps out at me. I'm training myself to think function derivative pair. And I look at this thing and I go, you know what? The derivative of the denominator is 2x, and the numerator is x. I have an approximate function derivative pair there. So let me rewrite this again. I'll rewrite this as 1 over x squared plus 2 times x dx. And I'm thinking this is going to be 1 over u, and this is going to be a constant multiple of du. That's what I'm thinking. So let's just go through the 5-step process. Composite function. Yes. 1 over x squared plus 2 is a composite function. And the reason is this is the same as x squared plus 2 to the negative 1. So really we have a function raised to a power here, and that is always a composite function. So here is the outer function, and the inner function is the raising of, the inner function is x squared plus 2. Our rule of thumb is to let u be the inner function. So that means that u is x squared plus 2. Now let's go to our second criterion. Do we have an approximate function derivative pair? And the answer is yes. We've already seen that. If we let x squared plus 2 be our function, then 2x is our derivative. And our rule of thumb in part B is to let u equal the function of the function derivative pair. So u is x squared plus 2. And then criterion C just says, do A and B suggest the same choice of u, and the answer is yes. So in criteria A, B, and C, if we get yes for each of these, U substitution is a cinch. It's definitely the way to go. And we answered yes to all three questions, so let the good times roll, right? So now we got to compute du. U is x squared plus 2. So du dx is 2x, and du is 2x dx. And I'm going to leave a little space for some scratch work that I'm going to have to do in step 3. And let me pause while I erase the board. Okay, I am ready to resume. My third step is to analyze my integral in terms of u and du. And remember, u is x squared plus 2. So here I have 1 over x squared plus 2. So this is going to be 1 over u. And here I have x dx. I don't have x dx here, I have 2x dx. So in order to make the right-hand side of this equation look like x dx, I'm going to have to take both sides of this equation and multiply by 1/2. So x dx, that's 1/2 du. In terms of u, this is 1 over u times 1/2 du. And our integrand has a constant factor here. We all know what we do with that. We bring it out in front of the integral sign. So we have 1/2 times the integral of 1 over u du. A constant times an integral, or a constant times an antiderivative. We write the constant down, and then we forget about it and compute the antiderivative. The antiderivative of 1 over u with respect to u, that's natural log of absolute value of u plus c. So now we can go back to where we left off in our integration process. We were trying to compute this thing, and we have it in terms of u. In terms of u, this is, oops, I better watch myself here. I'll write down the parts of the integral that we've already computed so I don't forget them. If anybody would forget something like that, it would be me. So I'm going to write these things down. X cubed, and you know what? Somehow I don't think this was a 2. Somehow I think it was a 3. I hope it was. X cubed over 3 minus 2x plus this hunk of junk here in terms of u, it's 1/2 the natural log of absolute value of u plus c. And if you're wondering why I had 2 plus c's here, I have absolutely no idea. I was writing and I wasn't thinking. No plus c here. When we do an integral, we only need one. So here it is. Now, my integral or my antiderivative is done. The only thing that I want to do now is rewrite it in terms of x. So I'll have 1/2 natural logarithm of 1/2 natural logarithm of the absolute value of u, and u was x squared plus 2 plus c. There's my answer. When I looked in the book, they had it in a slightly different form. If you're doing this on a test, if I'm doing this on a test, I'm going to leave it like this and go to the next exercise. But we want to make sure that we can make our answer match what's in the back of the book. And they did not leave it like this. And I'll tell you what they did. They used this property that if you have natural log of x to the n, you can bring the exponent out front like this. Well, you know what? This is an equation, which means it goes both ways. We can read it this way, or we can read it this way. So what this property also tells us is that if we have a constant times the natural log of something, we can write that as the natural log of that something raised to the power of the constant. And that's what we have here. We have the natural log of absolute value of x squared plus 2, 1/2 out front. So let's just rewrite it and make sure that we can get what they get in the back of the book. But on a test, if I'm doing this on a test, I'm going to stop right here, okay? So we have x cubed over 3 minus 2x plus 1, no. We're going to take this 1/2 and move it to the exponent. Natural log of absolute value of x squared plus 2 to the 1/2 plus c. And I'm not done yet. These absolute value bars, it turns out I don't need them here because x squared plus 2 is always positive. X squared is never less than 0. So x squared plus 2 is never less than 2. So I don't really need these absolute value bars here. So let me get rid of them. See that? I got rid of the absolute value bars, much better. So inside the natural log function, what I'm doing is I'm raising x squared plus 2 quantity to the 1/2 power. Well, if we're raising something to the 1/2 power, that's the same as doing what? Yeah, computing the square root. So I'm going to write this in terms of a square root, not because that's the kind of thing I'd usually do, but because that will explain how the people who wrote the book got their answer. And I think this is what they have. If I remember right, this is the answer that they had in the back of the book. So book's answer here, I think that's what they had. Our answer here, and again, if I'm taking test 4 and I get this, I'm stopping right here. If I'm on the final exam and I get this, I'm stopping right here. If I'm doing homework out of the book, I'm going to take this answer and make sure it's equivalent to what they have in the back of the book as their answer, just to make sure that I've done it completely right. Okay, let's see. That was exercise 21. Yeah. Exercise 17 is next. I'm sorry I'm doing them out of order. I forgot about number 17, but number 17 is coming next. Exercise 17. And in this exercise, we have pretty much the same kind of enigma that we had in 21. We have the integral of a quotient of polynomials where the degree of the numerator is greater than or equal to the degree of the denominator. So it's not in proper form. So the first thing that we have to do is long division of polynomials or synthetic division, just to rewrite this as something plus the quotient of polynomials where the degree of the numerator is strictly less than the degree of the denominator. So I'll write down my divisor, and I'll write it down here to give myself a little bit more room up above. And my dividend. And every power of x essentially is given its own place. X squared, x to the first, x to the 0. Good. Now we compare terms of highest degree, x and x squared, and we do the division that way. X goes into x squared x times. Multiply x by x squared plus 1, and we get x squared plus x. And subtract 3x minus x, negative 4x plus 2. And we repeat the procedure. Take the terms of highest degree. X goes into negative 4x negative 4 times. Negative 4 times x is negative 4x. Negative 4 times 1 is negative 4. And we subtract 2 minus a negative 4 is 6. X plus 1, 6 divided by x plus 1 is 6 divided by x plus 1. So this expression, x squared minus 3x plus 2 over x plus 1, is equivalent to x minus 4 plus 6 over x plus 1. Now, let me pause while I erase some of the board. Okay, so this is what we're actually computing the antiderivative of. Antiderivative of x is x squared over 2. Antiderivative of negative 4 is negative 4x. Antiderivative of, this is a quotient. You know what? I think I'll delay this computation until the next step. All I have left to do, though, is to compute the antiderivative of this term. And I think that is going to be a snap. You know what? I'm going to write this or rewrite this one more time. I'm going to move the 6 out front so that I have 1 over x plus 1 dx. Do I have a composite function? Yes. 1 over x plus 1, and that's the same as x plus 1 to the negative 1. So this is a function raised to a power. The power is the outer function. The x plus 1 is the inner function. And we let u equal the inner function here. Whoops. I'm going a little bit too fast. U is the inner function, so u equals x plus 1. And now, do we have an approximate function derivative pair? You know, this one's kind of got me stumped. I don't see a function derivative pair there. But just on the strength of part A, where I have a composite function, I'm going to go ahead with u substitution. Now, it may not work because I don't see an approximate function derivative pair. And maybe there is one there and I'm just not seeing it. Maybe that's it. I do see a composite function, so I'm going to go ahead with u substitution because, quite frankly, I don't know what else to do. But since I haven't satisfied criteria A, B, and C, it may not work. But again, since I don't know what else to do, I'm going to go ahead and try u substitution. And u is x plus 1. So I compute du, that's part 2. U is x plus 1. Du dx is 1. And du is 1 dx. And you know what? Now all of a sudden the mystery becomes, the solution to the mystery becomes apparent. I did have a function derivative pair up here. The function derivative pair was x plus 1 and 1. See, I have dx here, but that's the same as 1 times dx. It's just that when we have 1 times something, we hardly ever actually write it explicitly. We just know that it's there and we don't write it. But that's why I missed the approximate function derivative pair. There's a factor of 1 here that we just don't write. And 1 turned out to be the derivative of this function. That's why I missed it. But, things look good now. Things look very good. Give me a second to rewrite again. I'm back. And we go to step 3, analyze in terms of u and du. x plus 1 is our u, and dx is the same as du. So this is just 6 times the antiderivative of u with respect to u. Okay, step 4, integrate 6 times the integral of 1 over u du is 6 times the natural log of u, absolute value, plus c. And then I guess I also rewrite in terms of x. So what did I have? I had 6 integral or antiderivative of 1 over x plus 1 dx equals, in terms of u, this is 6 natural log absolute value of u plus c. In terms of x, this is 6 natural log x plus 1 absolute value plus c. So we are just about ready to wrap things up here. Okay, we have x squared over 2 minus 4x plus 6 times the integral of this garbage, which turned out to be 6 natural log of x plus 1 plus c. And I think our authors were kind enough to leave the answer in that form also. By the way, this business about integrating the quotient of integrating the quotient of polynomials, where the degree of the numerator is greater than or equal to the degree of the denominator. That's going to be a big deal in calculus too. We're going to see a lot more about integrating quotients of polynomials where the degree of the numerator is greater than the degree of the denominator. Just so that you'll know, I'm not going to give you that kind of an exercise on test 4. And I'm not going to give you that kind of an exercise on the final exam. If you're taking Cal 2, you're going to see it again anyway, and you'll have some experience working with the antiderivative or integral of the quotient of polynomials, in which the degree of the numerator is greater than the degree of the denominator. In Cal 2, they will have a little bit more time to beat that drum to death. And you'll learn how to deal with this because they're going to take exercises like this and do a lot more with them than we've done in Cal 1. So if you're taking Cal 2, you'll see this in Cal 2. I'm not going to test you on something like this in Cal 1. And if you're not taking Cal 2, well, you've seen something like this in the homework. Learn how to do it just to strengthen your mathematical and integration skills. But I'm not going to give you a question on test 4 or on the final where we have the quotient of polynomials where the degree of the numerator is greater than or equal to the degree of the denominator. That's just a bit much for what we're doing in Cal 1. If you need to know how to do that, you're probably going to take Cal 2 anyway, and you'll see it in Cal 2. So this kind of an exercise, you're not going to see it on test 4, and you're not going to see it on the final exam. Now let's do some more exercises. Before I start with exercise number 33, let me go through some common integration forms. The forms on the left we saw about 2 weeks ago, maybe 2.5 weeks ago. These antiderivatives we should know for test 4. We should know these antiderivatives for test 4 and the final. Antiderivative of sine, antiderivative of cosine, antiderivative of secant squared, cosecant squared, antiderivative of secant x tangent x and cosecant x cotangent x. Know these. We've had enough experience working with them that we probably should know these by now. The antiderivative or integration forms behind me, these are forms that can only be derived using the natural logarithm function. So for reference in doing the homework exercises on page 330, write these forms down. We're not going to have to know these forms for test 4 or for the final. If you take Calculus 2, you should learn these forms early on in the course. And you might know that, notice that the integral or antiderivative of tangent has 2 different forms. This is the universally accepted form. Every text in calculus on Earth, plus on other planets and other galaxies, have this is the antiderivative of tangent x. This is the universally accepted form. This is the form that we find in our text. It's correct. But we don't really seem to have it. We don't see it in the literature outside of our own text. Both of these are correct. This is the form that our authors have used for the last several editions of the text. This is the universally accepted form. I guess use whatever one you want. In the homework answers, believe it or not, sometimes they'll use this form, sometimes they'll use that form. They're not consistent. Also, for the antiderivative or integral of cosecant x, we have 2 forms. This is the universally accepted form in every text in the universe, even in galaxies far, far away. This is the form that you will see. In our text, apparently, this is the form that our authors use. Actually, I haven't looked, but this is the form that they used in one of the homework exercises. So I'm assuming that this is the form that the authors use in the text. If you're not taking Cal 2, don't worry about these forms over on the right. You won't have to know them for test 4 or for the final. If you are taking Cal 2, you won't see this on test 4 or the final exam of this class, but make sure you commit these forms to memory early on in Calculus 2. You'll have to know them. Now, on to exercise number 33. Exercise 33. First of all, the exercise is not given in terms of the variable x. It's given in terms of this variable. It's the Greek letter theta. If you're going to stay in the mathematical sciences, you should probably commit the name of that variable to memory, it's best if we do that, if we have the names of the lowercase Greek letters committed to memory. And this is one of them we should know. Pretty much by convention, theta is used to represent the measure of an angle. So we're going to see theta in trigonometric functions. Now, having said that, let's get on with our exercise. Let's see, is U sub appropriate? Do we have a composite function? And the answer is yes, because the inner function is not the variable theta itself. It's some constant times theta. So cotangent is the outer function. Theta over 3 is the inner function. And by our rule of thumb, we let U equal the inner function. Now the next criterion, do we have an approximate or an exact function derivative pair? And the answer is yes, believe it or not. We don't see it there, but we learned something from one of our previous exercises. I think it was the last one. You see this thing here? What's the derivative of 1/3 theta? It's 1/3, right? Ooh, but we don't see 1/3 outside here. But there is a constant multiple of the derivative of this function out here. It's just that we never write it. 1/3 theta, its derivative is 1/3. This is a constant multiple of the derivative of this function. So, yep, we're not going to be fooled by that again. So 1/3 theta and 1. Here's our function. Here's our derivative. And our rule of thumb is to let U equal the function. So U equals 1/3 theta. So we have the same U for A and B. And do criteria A and B suggest the same choice of U? They do. Theta over 3 and 1/3 theta, they're exactly the same. So on we go to step 2, compute du. U equals theta over 3 or 1/3 theta. So du d theta is 1/3, and du is 1/3 d theta. And we'll leave a little space below for step 3. Step 3, that's not a 3. Analyze in terms of u and du. So we have the antiderivative or integral of cotangent of 1/3 theta and d theta, which we know is the same as 1 times d theta. Here is cotangent of u. And that thing, well, let's see. We don't have 1 d theta anywhere, but we do have 1/3 d theta. And we can make the right-hand side of this equation look like 1 d theta by multiplying both sides by 3. And remember, 1 d theta and d theta, they're the same thing. So this is 1 d theta, that's 3 du. And our antiderivative turns out to be antiderivative of cotangent u times 3 du. And this constant factor inside the integrand, we're going to move that out front. 3 times the antiderivative of cotangent u du. Now this is one of those integrals that we don't have to know for test 4 or for the final exam. But we want to do it now, and we can look in our book to see what the antiderivative of cotangent should be if we don't know it. We want to do it now just for the practice of integrating and computing antiderivatives. 3 antiderivative of cotangent u du is equal to 3 times something. And let's see, what is the antiderivative of cotangent of u? It's the natural log of sine of u plus c. Okay, we integrate. Now, we have to rewrite it in terms of the original variable. Give me a second to erase some of the board. In terms of u, our answer is 3 natural log of sine of u. 3 natural log sine of u plus c. We just have to rewrite it in terms of theta. And we recall that u equals theta over 3 or 1/3 theta. So our answer is 3 natural log absolute value of sine of u, which is theta over 3, plus c. And I sure hope that's right. Probably is. Okay, what's on our agenda now? What was that? Number 33. Okay, number 35, I guess, is coming up. Okay. Let's take a look. I see cosecant as a function of x, but it's not cosecant of x, it's cosecant of 2x. So technically, this is a function evaluated not at a variable, but at another function. So I'm thinking composite function, use u substitution. Is u sub appropriate? And the first thing we do is look for a composite function. And we do have one. Cosecant evaluated at 2x 2x is the inner function. And our rule of thumb says, let u equal the inner function. So u equals 2x. Now, what about an approximate function derivative pair? You know, it seems like we're seeing a lot of these kinds of exercises in the homework. Doesn't look like there's a function derivative pair at first, but this thing is cosecant of 2x times 1 dx. And this is going to be our derivative. It doesn't appear explicitly in the original form of our exercise, but anytime we have an expression like cosecant of 2x, we can always multiply it by 1. We don't change the value. So even though we don't see a factor of 1 here, it's here. And this is going to be approximately the derivative of the inner function. Why we're seeing so many of this kind of exercise right in the beginning of integration, I don't know. Unless our authors are a couple of snakes in the grass and they really want to make us suffer. That could be. The function is going to be 2x, and the derivative is going to be 1 approximately. So 2x is the function, and 1 is approximately the derivative. And our rule of thumb says let u equal the function. So u will be 2x. And then for criterion C, do A and B suggest the same choice of u? 2x, 2x, they sure do. We are definitely going in the right direction. Let the good times roll. Next thing we do, compute du. U equals 2x, du dx is 2. So du is 2 dx. And we'll leave a line blank afterward. Next thing we do, we analyze in terms of u and du. So we have cosecant of 2x dx, and we know what's going to happen here. We're looking for the derivative of 2x outside here, and it is here, it's just disguised. There's always a factor of 1 wherever we want to put it, and this is going to be our derivative. We decided that u is 2x, so this is the cosecant of u. And 1 dx, well, I see 2 dx here. I can make the right-hand side look like 1 dx if I multiply both sides by 1/2. So 1 dx is 1/2 du. Cosecant of u times 1/2 du. Now let me ask you something. what do you think we're going to do with this factor of 1/2 in the integrand? If you said move it out front, in front of the integral sign, you're absolutely right. So this is what we have. 1/2 the antiderivative of cosecant u du. Step 4, integrate. One-half antiderivative of cosecant u du is 1/2 times something. Now this is an integral form that we're not responsible for until we start taking Cal 2. The antiderivative of cosecant u, and this is one of those forms where our authors have a different form for this antiderivative than the rest of the world and the rest of the universe. Our authors for this particular antiderivative have as the antiderivative negative natural log of cosecant u plus cotangent u. No one else on Earth or in the known universe does, but this is the form that our authors use. And it is correct. It is correct. It's just not what the rest of the universe uses as the standard form. So what do we get? We get negative 1/2 natural log cosecant u plus cotangent u plus c. And now that we're going to rewrite this. Okay, we're back. We have to rewrite this in terms of the original variable, which was x. In terms of u, our answer is negative 1/2 natural log absolute value of cosecant u plus cotangent u plus c. Well, what was u? If you remember, u was 2x. So this is going to be negative 1/2 natural log absolute value cosecant 2x plus cotangent 2x plus c. That's the book's answer. And oddly enough, I don't think that they did anything about this negative 1/2 out front, like rewrite it in terms of a square root or something like that. I think this is the form that our authors left the answer in. And if I'm doing this on a test, I'm probably going to stop here too. I'm not going to take this negative 1/2 and turn this into the natural log of 1 over square root of garbage. If I get here on a test, I'm going to stop and go on to the next exercise. Okay, here's our next exercise, and we're doing this with respect to the variable theta. We're computing the antiderivative or the integral with respect to theta. And we have the antiderivative of the difference of two terms. So that we do the antiderivative of the first, which is 5 theta. If we were doing this with respect to x, the antiderivative would be 5x. But we're doing it with respect to theta, so the antiderivative is 5 theta. And then we have the antiderivative of cosine of 3 theta. That's a composite function. So you know what? I'm going to go through the U substitution drill because that's what we have to do for this thing. So 1A, composite function. The answer is yes. We have cosine evaluated at 3 theta. And the inner function is 3 theta. And our rule of thumb says, let U equal the inner function. So this means U equals 3 theta. Now, do we have an approximate function derivative pair? Oops. This is exactly the same kind of exercise as 35. And exactly the same kind of exercise as 33. So I don't need a ton of bricks to fall on me before I get the point, usually. I'm going to smarten up and I'm going to say, you know, this is antiderivative or integral of cosine of 3 theta. And there's a 1 here. There's a factor of 1 right after cosine of 3 theta. And I'm doing this because I know that the derivative of 3 theta is going to be a constant. It's going to be 3. And 1 is a constant multiple of that antiderivative. I'm sorry, 1 is a constant multiple of the derivative of 3 theta. So I'm not going to pretend like I don't know that this factor is there. So, approximate function derivative pair. Yes, 3 theta and 1. 3 theta is the function, and 1 is approximately the derivative of 3 theta. We're only off by a constant multiple or a constant factor. So our rule of thumb is to let U be the function of the function derivative pair. So U equals 3 theta. And then finally, do criteria A and B suggest the same choice of U? U equals 3 theta, U equals 3 theta, yes. So we are definitely barking up the right tree here. Let's move on to part 2, compute du. U equals 3 theta, du d theta equals 3. Du equals 3 d theta. And we'll leave one more line blank for our scratch work later on. Next, we're going to compute. No, next we're going to analyze in terms of U and du. And I'll forget about the negative sign here for now. I'll remember it's here later on. We'll just look at the antiderivative of cosine of 3 theta. Remember, U is 3 theta, so this is the cosine of U. And let's see. I'm forgetting the plays in my own playbook. Instead of d theta here, why don't I write 1 d theta? especially since I made such a big deal about it 2 minutes ago. I don't have 1d theta here, I have 3d theta. But if I multiply both sides by 1/3, I'll get 1d theta. So 1d theta is 1/3 du. And our integral becomes cosine of u times 1/3 du. And what am I going to do with that constant factor in the integrand? If you said move it out in front of the integral sign, you're right. So take this 1/3, get it out of the way, move it out in front of the integral sign, and we get 1/3 the integral or antiderivative of cosine of u, cosine of u du. Now, step 4 is to integrate. An antiderivative of cosine, we're supposed to know that. That's going to be sine of u plus c. So all we have to do now is rewrite our answer in terms of the original variable, and we'll do that in just a second. Okay, we're back. We have as our answer 5 theta minus the antiderivative of cosine 3 theta d theta. And we know what this antiderivative is in terms of u. It's 1/3 sine of u plus c. All we have to do is write it in terms of theta. And if you remember, u equals 3 theta. So 1/3 the sine of u becomes 1/3 the sine of 3 theta. And this is our final answer, 5 theta minus 1/3 sine of 3 theta plus c. Now I think we still have a couple more. I was asked to do number 39 and number 41. So here they come. Take a look here. Look at the entire denominator, 1 plus sine t. And look at the numerator. The numerator is the derivative of the entire denominator. Now, we could also say that part of the denominator, sine of t, is a constant multiple of the derivative of the numerator. So which way do we go on this? Well, here's what we do. We have a known integration form or a known antiderivative form for the case where we have the function in the denominator and the derivative in the numerator. We don't have a known antiderivative or integral form for when we have the function in the numerator and the derivative in the denominator. So the way we want to look at this is function in the denominator, derivative in the numerator, because that fits a known integration or antiderivative form. So I'm going to rewrite this expression this way. 1 over the denominator times the numerator And now when we go through the drill, composite function, yes. 1 over 1 plus sine of t. And it's a composite function because we can look at that as 1 plus sine of t, all raised to the -1. It's a function raised to a power. So that's one explanation that we could give for why this is a composite function. And the exponent is the outer, and 1 plus sine of t is the inner. Our rule of thumb says let u equal the inner function. So u equals 1 plus sine of t. Now, do we have an approximate function derivative pair or an exact function derivative pair? Either one. And the answer is yes. Cosine is exactly the derivative of 1 plus sine t. So 1 plus sine t is our function, and cosine of t is our derivative. And our rule of thumb says let u equal the function of the function derivative pair. So u is 1 plus sine of t. And then we might want to check. Do A and B suggest same choice of u? U equals 1 plus sine t, u equals 1 plus sine t. Wow. The fact that we can answer all three of these with a resounding yes means that u substitution is the way to go, and our choice of u is correct. So what do we do now? To compute du. U equals 1 plus sine of t. du dt is cosine of t, and du is cosine of t dt. And for my next step, I guess I'm going to analyze in terms of u and du. So I have 1 over 1 plus sine of t times cosine of t dt. U is 1 plus sine of t, so this is 1 over u. Du is cosine of t dt. This is du. So our integral becomes 1 over u du. And I guess I could go to step 4. We know what this is. This is a known form. It's natural log of u plus c. Okay. We're almost done. Let me erase some of the board. Okay, we're back. We know what our integral equals in terms of u. It's natural log of u plus c. And now we want to remember that in step 2, we let u equal 1 plus sine of t. So all we do is substitute 1 plus sine of t for u, and here's our answer. 1 plus, should have left well enough alone. 1 plus sine of t plus c. Okay, but we've gotten a lot done today. Just one more exercise to do. It's number 41. Okay, antiderivative of secant x tangent x over secant x plus 1. And something's ringing a bell here. Secant x tangent x, I recognize that as being the derivative of secant. So the numerator is the derivative of secant, but in a slightly broader sense, the numerator is the derivative of the entire denominator. The derivative of secant x minus 1 is secant x tangent x. So I have an antiderivative in the form of derivative on top, original function on the bottom. And we know how to integrate that. So I'll rewrite it so that I have 1 over the function. And then after that, I have the derivative of the function. And this is going to be a snap. We've already made the crucial observation that this thing is the derivative of the denominator. So let's just go through the 5-step drill again. Step A, do we have a composite function? And we sure do. 1 over secant x minus 1, that's the same as secant x minus 1 to the negative 1 power. And anytime we have a function raised to a power, that's a composite function. So the raising of something to the minus 1 power is the outer function, and secant x minus 1 is the inner function. Our rule of thumb says let u equal the inner function. So u is secant x minus 1. And now what about a function derivative pair or an approximate function derivative pair? Well, we've seen that already. Secant x tangent x is the derivative of the denominator. We have that. And it's an exact function derivative pair. Secant x minus 1, that's the function. Secant x tangent x, that's the derivative. And the rule of thumb in part B is let u equal the function of the function derivative pair. So u is secant x minus 1. And criterion C, do A and B suggest the same choice of u? They sure do. So we know we're doing everything right. Second step, compute du. U equals secant x minus 1. Du dx is secant x tangent x, and du is secant x tangent x dx. Next step, analyze in terms of u and du. And we have integral of 1 over secant x minus 1 times secant x tangent x dx. Remember, u is secant x minus 1. So this much is 1 over u. And du is secant x tangent x dx. So this is exactly du. So we have the antiderivative of 1 over u du. And this is a known form. Let's not bother with step 4 and so forth. We know what this is. This is natural log of u plus c. So we'll do our final step as soon as I clear some space from the board. Okay, let's tie up some loose ends. Remember that our integral in terms of u is natural log of u plus c. And remember also what u was. U was the secant of x minus 1. So plugging this in for u, we're going to get natural log of secant x minus 1 plus c. That's the exercise in its entirety. Everybody, I hope this helps, and have a very productive rest of the break. Get done as much as you can. Study hard. As a matter of fact, study hard until the end of all final exams. As our football players know, they leave it all on the field. They don't have anything left over. Let's leave everything on the field when it comes to preparing for finals, and then we can go home for a nice long break and know that we did everything that we could, no regrets whatsoever. And of course, we're not just leaving it on the field for the sake of leaving it on the field. We leave it on the field for the sake of winning. So let's knock ourselves out from now until the end of finals, and let's make sure we ace everything.